Right, so hello everyone, good morning, good afternoon, whatever the case might be, and welcome to the Center for Theoretical and Computational Physics weekly seminar. And today it is a pleasure to welcome Emanuela Gado from Georgetown University in Washington, DC, United States. So Emanuela did her PhD at the University of Naples in Italy. This was followed by a postdoctoral appointment first in Montpellier, France, and then at ETH Zurich in Switzerland, where she stayed on as a staff member before later joining Georgetown University, where she's now an associate professor. And today she's kindly agreed to tell us about her work on the physics of cement. So before I hand over to Emanuela for this exciting and intriguing topic, just a couple of announcements from me. First, this seminar is being recorded, so by staying on, you're giving permission to your voice and image being recorded and stored. Second, in the interests of internet stability, can I ask all of you, except the speaker, of course, to mute your microphone and turn off your camera during the seminar. If you wish to ask a question, you can, of course, unmute yourself and switch on your camera if you so desire. So, without further ado, it's over to Emanuela for the seminar proper.
Thank you. It's really a pleasure to be here. And I've met with a few of you when I came to visit last time, and I hope that we will be able to meet soon again in person, either in Lisbon or in Washington. So I want to talk about cement and in particular the physics of cement cohesion. Basically, cement is the material that we get from these bags. It's the powder in the bags that we mix with water, and over a few hours it turns into a very hard solid. In this transition from liquid to solid, it's what we are interested in, right? Because this is what we use for construction. The powder itself, it's made of micromatic grain, which are basically calcium silicate hydrates, which are basically calcium silicates, as you see here. And then with the mixing the cement and water with rocks, sand, and other small aggregates, basically that's how you make concrete. And concrete is the most used material on Earth. It's the material that we use for construction. And it's the only material that we actually have to do something like that. So the question that emerges, because we use so much of this material and because its use, it's so unavoidable for our built infrastructure, is that actually if we consider the projection of for example, the United Nations organization about increase of population, then we realize that basically within now and 2050, the idea is that we will need to build something like 9 to 10 cities of the size of New York each year in order to meet the need of this population in terms of built infrastructure. And so the question about how this development is sustainable becomes a lot the question of how is concrete sustainable, and even more, how is cement sustainable? Because in fact, while we are doing this, and while concrete is the only material that we have to basically do this in a safe and reproducible manner, construction materials are responsible for sizable amount of CO2, and in fact, basically up to 8% of the whole man-made CO2, it's actually derived from the production of cement for concrete. So the reason is because, in fact, just let me add to this, that the number become even more impressive if you consider that actually China over 3 years, between 2011 and 2013, has actually consumed and produced more cement than the US in the whole 20th century. So this tells you what is the size of the problem. And the reason, as I was saying, the reason why this happens is that actually to produce cement, to make this calcium silicates that actually are the powder that we use to mix with cement, to mix with rocks and sand and water, you need to burn at very high temperature calcium carbonates and other minerals. This is a process that in principle it's very convenient. It was invented in the beginning of the Industrial Revolution. It is very convenient because now you can make cement, you can produce this calcium silicate everywhere on Earth using minerals that are available everywhere and in big quantities on Earth. But then you need to burn them at very high temperature in these huge kilns. And this process actually in which you extract the calcium from the calcium carbonates leads to this huge release of CO2, huge due to the volume of the cement that we use. So the question is really, can we reduce, can we do the same thing? Can we meet the needs of the infrastructure, of the update of the current infrastructure, of the new infrastructure that we need to build? Can we do this in a smarter way, reducing actually the amount of cement that we use, maybe changing the production of cement in a way that is more sustainable and greener? And so in order to understand how to do this, we need inevitably to understand how this material works. And whereas there is more than a century of use of this material and more than a century of investigation of these materials, there are still gaps in the fundamental physics, in understanding the fundamental physics that control its functioning. And this is where actually things can be done to devise more sustainable practices and more sustainable formulations. So the reason why we actually produce this powder is that it's very reactive with water. When you mix it with water, the grains of the calcium silicates dissolve, immediately start to dissolve. And from the dissolution of the grains, there is another material that actually form and precipitate. And this is what is called calcium silicate hydrate, or calcium silicate or CSH, which precipitate in the form of nanoparticles. And these nanoparticles now are very sticky. They stick together into a gel-like structure that fill the space and literally glues together cement and all the different components of concrete into a solid that it's basically as hard as a rock and that we can use for buildings, bridges, and all sorts of, and all our infrastructure. So the question that basically are put forward at this point are, how can we reduce the CO2 footprint of this process and of this material without compromising the mechanical performances? Ideally, we would like to enhance the mechanical performances so that we can do more with less. And this could be a very interesting direction to, and one of the strategies that we need to pursue. The other option is actually to try to change the chemical composition of this material and try to come up with a composition that doesn't require such a process that releases this big amount of CO2. So why this is not easy? Well, the question is that basically at the very small scale, this material, as I said, precipitates as nanoparticles. These nanoparticles have a layered structure that, in fact, it's very similar to a structure of a rare mineral called tubermorite, as it was recognized already by Bernal several years ago. That then, and the nanoparticles then form an amorphous structures, which then aggregates into this type of gels that has a fine pore distribution and very wide pore distribution. So all this, the tricky part, because this is a solid that forms in very non-equilibrium condition and whose mechanical properties at different length scale are very hard to predict. So it's very hard to understand how to change the chemistry and how to change then in ways that then modifies the aggregation process, which then modifies the final the properties of the final product. So that's where, as I was saying, we need to intervene to have, there are gaps in the understanding of the fundamental physics that we can try to fill to come up with new ideas and more scientifically designed strategies to make this material better and the use of this material better. So in fact, the properties of the gel, the fact that the nanoparticles aggregates into a disordered non-equilibrium structure and the solid is this type of solid, it shows up in the mechanical properties of the material, as I will show you in a minute, but it's also, it shows up for sure in how strong the material is, how cohesive the material is, and these are the first question that I want to address, but it even affects the very long time behavior of the material. So in fact, understanding the physics of how this precipitation and gelation works, in fact, has consequences, not just for the strength of the material, but for the durability of the material and of the infrastructure. For example, one proof of that is that, in fact, concrete and cement are solid materials that are characterized by creep. And these are the experiments of my colleagues at MIT that have actually measured some years ago the creep compliance rate, so the evolution of the flow properties, also of the deformation rate in a material that is actually solid. Of course, this rate is very, very small, but in fact, if you consider that you want to be able to use the building, the infrastructure for a very long time, then you start to worry about that, because this phenomenon, in fact, has connection with maintenance costs and really trying to design materials and structure that can last better in different environmental conditions over long time scales. Okay, so the formation of the gel, in fact, it's associated, of course, with the development of the mechanical strength. And these are measurements with ultrasound of the evolving modulus of the material in which the gel is actually forming and progressively densifying and solidifying, because the nanoparticles that compose the gels, actually, they keep precipitating in the porous solution as the grains continuously dissolve over time. And you can also see that this evolution of this of the mechanical strength of the shear stiffness here, it's actually very it has a first fast increase, then it has some sort of plateau, and then finally it increases to the strength that we need for making the building stand still. And the evolution of the mechanical strength is actually coupled to this precipitation of the process, which is characterized, which is basically is related to this exothermic reaction that leads to it's underlying the production of this calcium silicate hydrate. And so you can follow the reaction with calorimetry, and you can see that the heat flow is actually also really has a non-trivial profile over time. It has an acceleration and deceleration period. So it is a complex process in which different actually chemical reactions are intervening and different physical phenomena develop. In the end, you end up with the material. This is small angle neutron scattering data from the hardened CSH, where you can see a signature of this nanoparticles. And then you can see this enhance the intensity and low Q, even when the material is completely hardened and basically homogeneous, and very dense. So even when the material densifies and becomes as homogeneous as it can, there is still traces of this hierarchical organization of the structure that comes from this very complex aggregation that leads to the gel formation. Okay, so now that I've laid out the problem of the physics that we would like to understand, what I would like to do is to talk about three aspects. The first is, where does the cohesion of the material come? Because for sure, this is a very important aspect. The reason why cement is used is because it's extremely sticky. So where does the stickiness come from? The second point is, okay, once we understand the cohesion, how can we then use this understanding into modeling, understanding, rationalizing the formation of the gels, and then the development of the characteristics of the gel. And then once that we have understood some of the physics that is involved in there, how can we, sorry. Okay. Once that we understood these two steps, is it really something that is going to be useful for the material as we use it in the infrastructure? Okay. Feel free to interrupt me at any time and ask questions. So why is this material sticky to start with? Well, you have these nanoparticles that precipitate. And in fact, even at the very small scale, cement, it's particularly complicated material. I said that the structure, it's similar, the nanoscale structure, it's really nanoscale structure, it's really similar to a rare mineral called tubermorite, although with tubermorite you cannot actually make cement. And this has been studied. There is now a large literature on atomistic simulation of this material. But in the end, the cohesiveness of the material comes from the fact that the surfaces of the nanoparticles, they are very sticky with each other, and they are immersed in this in water and the ions that are continuously produced by the dissolution of the grains. So, in fact, if we look at what happens at this, between two nanoparticles, so you have actually the surfaces of the nanoparticles that are negatively charged, and the surface charge evolve as cement hydration proceeds due to the underlying chemistry, and so you have these negatively charged surfaces with ions, with counter ions in between, which are mainly calcium ions, and so you have basically like charge attraction. But in fact, it's not uncommon in colloidal systems. Some of this, for example, can be understood, as we know, with the LVO theory. But in this case, this picture, it really does not apply, because the surfaces, as I said, they have quite high negative surface charge. And the counter ions in between are mainly calcium ions, which are divalent. In fact, if you use the LVO theory to compute the net interaction in this type of system, you basically get only a repulsive. That only a repulsion is possible. So, in fact, then what this means is that the cohesive interaction, they must come from whatever the LVO does not include. And so they must be the result actually of strong ion correlation forces that are present in the system due to the high surface charge and the fact that you have divalent or multivalent ions. And so the point is that you can do then, you can put these ingredients in Monte Carlo simulation, as it has been done, to see that in fact for the surface charge, for the type of ions that you have in CSH, these are data from a study done on clays, and you can see that there are regions actually of this phase diagram where you have the interlayer distance and the surface charge density that corresponds indeed to calcium silicate hydrate, where you end up having the attractive interaction. So in terms, if you look at these ion correlation forces, indeed you can have an indication that the material should be sticky. However, the strength, the cohesive strength that you get from this type of calculation are relatively weak, very weak, to be able to justify the use of cement in construction. And basically, they do not justify a building being able to hold its load. So what we have done is actually to consider that what you would really want to do is in fact to consider the two surface charge, the two charged surfaces with the calcium ions confined between them. But the fact that the medium in which they are immersed, it's not a bulk dielectric medium, but it's actually water. So we have performed simulation. This is mainly the work of my student, Abey, actually. I insist in saying my student, but is now a postdoc at NIST. So during his thesis, he devised this model in which we also consider basically explicit water. We used SPCA water, and we did some tests also with TIP4P water to make sure that our results were not the specific, they were not affected really by the choice of the model. And so when you do this and you do three-dimensional simulation of these charged surfaces with the ions in between and with explicit water, you realize that actually the situation is quite different, because in fact the ion and the water structuring in confinement changes completely the net forces between the two surfaces. Basically, what happens is that there are ion water structures that become specifically stable at different degrees of confinement, and these ion water structure actually they do two things. They optimize the packing of the confined system in between the two charged surfaces. They dramatically decrease the dielectric screening of water in this very small space, because all the water that is there is bound in this ion water structure. And this makes the interaction, the cohesive interaction between the two surfaces to grow by 2 orders of magnitude. So here's the plot of now the net pressure that we obtain between the surfaces. This data up here is what you would obtain, just by the ion correlation forces that I was showing you before, where you consider just the ion in this dielectric continuum that has properties of bulk water. And these instead are the data that you obtain with explicit water. And this continuous line is actually a theoretical prediction for the effective interactions between the two surfaces that we have computed with our colleagues in France, considering that now the electrostatics should be computed in terms of this ion water structure that we obtain from the simulation. So that if we consider this type of structures that then determine the net electrostatic interaction between the two surfaces, then you obtain these forces that actually follow pretty well what we have, the calculation from the simulation. And ultimately, as I said, we did also some tests with different water models, so you can see that the results do not depend on the specific water model we have used. And the theory allows us to really abstract the basic origin of this behavior from the simulation. So if we consider the correlations between the ions in this very strong coupling regime, and we compute the interactions between the two surfaces due to the presence of this stable ion water structure, then we obtain the forces that we basically see in the simulations. We can also use the theory to predict the amount, the fraction of bound water that is present in the system at different degrees of confinement from this theoretical prediction, and then compare it with the data in the simulation, and they actually agree quite well. So how does it work? Well, basically what you see, as I was saying, is that at a high surface charge, in presence of high surface charge, the ions are basically squeezed close to the surfaces, and they form this sort of hemispherical structures, hemispherical hydration shells with the water, and the stability of this structure actually change with the degree of confinement. And basically, as you increase the confinement, the stability of this structure becomes higher and higher. And so as you decrease the space available, what you basically get rid of is water that is sort of bulk-like because it's free. And all the water that remains is the water that it's basically very persistently bound to the atoms, to the ions. And so as you increase more the degree of confinement, you select a different type of structure depending on how much water is available and how much, which structure you can actually pack in the more and more confined space. So this phenomenon actually has two consequences that are very important for cement, because they explain two very strong observations that have been done in experiments over the year. One is the fact that the forces between the surfaces, the cohesive forces of cement, are actually very ion specific, which makes, in fact, changing the chemistry and coming up with greener formulation very tricky and difficult to do. But this understanding can now open new ways to see how to do this. So because this packed structure, the way the structures are packed, depends not only on the ion balance, of course depends on the ion balance, but it also depends on the ion size. So these are really truly ion specific forces, which ion specific structures, which qualitatively and quantitatively change if you consider different type of ions. Also, the other very important consequence is that, in fact, because the role of the water changes and the dynamics of the water changes as we go in this direction, increasing the confinement of ion and water in between the two surfaces, as I was explaining, then you start to see basically two populations of water. One population of water that is characterized by relatively fast dynamics that, in fact, has been detected in experiment in using scattering and, for example, NMR. And so you can see that there is a free water, a population that they call free water, and the population of water that you call bound water, that you can clearly distinguish them from the dynamics. So in the simulation, in this type of simulation, we can actually compute the dynamics of the water for different degrees of confinement. And so we can create this direct connection with the experimental observation that basically confirms that what we see is relevant to what happens in the real material. These forces, this phenomenon, so the structuring of the ions, the stability of different type of ion-water structure, and the water dynamics depends on the type of ion, as I was saying, depends on the degree of confinement, but it depends also on the surface charge, because depending on the surface charge, ions are more or less squeezed and more or less dense in the two layers that they form, more closer or less close to the surface. So depending on the surface charge, there are different type of ion structures that you can pack. And this is important for cement hydration. Why? Because during cement hydration, as I was saying, the surface charge of the nanoparticles actually increases over time. This is actually a very important characteristic of the development of the cohesion in this material. And so you can see that in our calculation, we can actually distinguish from what happens at early times where you have relatively lower surface charge. So with relatively lower surface charge, the ions are less squeezed close to the surface. So at relatively large confinement, you can still accommodate full hydration shells, very similar to those in the bulk at relatively large separation of the two surfaces. And then when you start to increase the confinement, basically you can stabilize the system and get cohesion by changing the hydration, the water ion structure, right? What happens here? But then you need to basically break this hydration shells, and this produces that this effect can produce intermediate range repulsions that are in fact seen in AFM measurements of surface forces between CSH nanoparticles during cement hydration. So basically with this type of calculation, we get a full, even if we have a very simple representation of the surfaces that are just represented with basically their surface charge, and we use a relatively simple model for the water, but we have a full representation, or I would say complete enough representation of how this phenomenon change with the surface charge, with the degree of confinement, and with the type of ions, to understand not only just why the material is cohesive and how cohesive it is in the end of the process, but also how interactions evolve over time as the surface charge density of the material change. And so now you end up with a different pressure profile between the two surfaces as you basically increase over time. As I said, you can understand basically that interactions can combine short-range attraction and repulsion in the very beginning, and then the attractive part becomes more and more prominent due to the phenomenon that I was telling you about. And this type of profiles and the change of the profiles over time closely resembles actually the first measurements that were made nearly 20 years ago by the group in Dijon, where they had an AFM tip on which they grow CSH, and they use it to poke on CSH produced during hydration of a cement grain surface in a very nice set of, I would say, pioneering experiments. So now that we have this connection and some understanding from about how the chemistry and the physical chemistry of the system actually leads to this very strong cohesion and this coexistence of attraction and repulsion of short range, we have some new ingredients to ask the question, how does this enter? Now, how the knowledge of this, knowing these forces and understanding this evolution of the cohesion of the material actually affect the formation of the CSH gels. And so what we have done is to design an approach in which we can now study the development of these CSH gels very much in a soft matter, coarse-grained type of approach, in which basically we model the CSH nanoparticle precipitation with a grand canonical Monte Carlo type of process, where now the chemical potential, you can think about it as basically the free energy gain for producing one of these nanoparticles. So for the production of one of this cement hydrate nanoparticles during cement hydration. And we combine this grand canonical Monte Carlo scheme with the molecular dynamics simulation, in which we can use the interactions that we know how to connect to the physical chemistry of the initial powder mix, to basically study how the precipitation of the nanoparticles interfere with the interaction of the nanoparticles in solution, and how this changes the way the gel forms. So what we have done is to use this type of scheme with considering a different type of interaction. These are a simplified version of what I was showing you, that, you know, the profile that I was showing you, in which basically what we studied is how the presence of this intermediate range repulsion, which can appear in the very early stages of dehydration, how the evolution of this intermediate range repulsion that goes away over time because interactions, as we have seen, become more and more just purely cohesive. How does this affect the formation of the gel? Basically, this is the question that we have. There is just one thing that I would like to add. This combination of grand canonical Monte Carlo and molecular dynamics actually allow us to change the rate, to study how changing the rate of this precipitation can drive more or less far from equilibrium the formation of the type of structures that we would obtain in just in molecular dynamics, if we would do like a molecular dynamics simulation as you would do for a normal colloidal gel, where you have a certain amount of particles that are present there from the beginning, and they just aggregate and gel depending on the interactions. So in a first study that I'm showing you now, what we have done is basically to fix one type of interaction. For example, this with the first, this relatively higher intermediate repulsion, which should correspond to very early stages of the cement hydration. And then we study how the precipitation actually leads to different type of gels for this interaction. And then we switch with interaction with less of this intermediate repulsive part, so that it's purely more and more purely attractive, which should correspond to later stages of dehydration. So when you do this, basically what you get here in this movie, what I'm showing you is the precipitation as it occurs during the simulation. And what you're seeing is just the link between the nanoparticles just for clarity. The color represents the number of neighbors that each particle gets bonded to. And so you can see that you started from the beginning, you have formation of this type of fibrils, which then branch and form into a network. And now the network has some sort of more homogeneous pore size and then continuously densify. If you look at what happens with interaction, so these are corresponds to the aggregation and gelation process with interactions that are very typical of very early stages of dehydration that have this relatively high repulsive shoulder. And on the right, you start to see the movie of the same thing happening if the forces are instead typical of what happens at later stages when surface charge goes higher and the interactions become just more and more a very deep attractive well. And so what you see that also in this case, you start to form aggregates, and then these aggregates branch into a gel, which has some porosity, and then this gel densifies more and more. And so what we notice is that actually for the same type of precipitation rate, the aggregates that you get here on the right are much bulkier and locally denser. And then the gel that you form, actually it's more heterogeneous and it has larger pores. So you start to understand actually a very interesting thing, I think, that the sequence of how the interactions evolve over time during the cement hydration has an impact in the development of the properties of the gel in a way that it was not necessarily obvious to understand in the beginning, because basically the fact that you start from a lower surface charge where you can have this intermediate range repulsion leads to a very fast growth of these fibrils, which are favored by this type of interactions. And then the fibrils branch to form a gel. So the growth of the fibril now it's very fast. And in fact, it's a process that we can map into the acceleration of the gel formation that I showed you in the beginning. And then the gelation that occurs in presence of this interaction actually favors very early stages percolation and therefore mechanical properties. So I can start to have a somewhat solid material very early. It also allows me to set some preferred size of the pores, which then remains, whose traces somehow remain in the following structure of the gel. On the other hand, the fact that I start from interactions that are these interactions that become now more and more attractive, when the interactions are actually more attractive, what I get is a gel that tends to be much bulkier. In fact, this type of interactions that characterize rather the end of the hydration process, and they take over when at later stages of cement hydration, they favor actually further densification of the material. And so this sequence, we can think about the sequence in time of what happens during cement hydration to go in some sort of diagonal direction this way across those processes. And this is important. Why? Because I already told you that the fact that you have these interactions in the beginning actually favors early stage percolation and development of mechanical strength and setting the pore size. Later stages, which are characterized by more and more attractive interaction, actually favor local densification of this network even more than what you would have if your interactions had remained the same. And so this, in fact, it's very important because the fact that the material reaches such high strength that it's basically mainly captured really by the contact between two nanoparticles, it's really due to the fact that the material is able to densify even when it reaches, continuously, even at much later times, and even when basically already percolated solid structure is set. And so this, the fact that the material, the structure, microstructure of the material evolves in this way with this type of underlying processes allows us to understand actually what is observed in cement hydration. And it provides a new framework in which we can understand what are the properties that we need to pursue if we want to change the chemistry of the system, but still keep this type of path in order to guarantee that the material has in the end the desired properties. And I will come back in a moment to that. The other thing is that now we can really see that these early stages of the material, when the material is really a soft matter, and I would call it a soft matter in construction because it's really a soft, solid material that it's being built, this is really now it's a very interesting regime in which we can intervene to make the material stronger, to adjust the pore sizes, which then have consequences for both increasing the mechanical properties of the material to make more with less, and to increase the durability of the material through its interaction with the environment. In this type of simulation, the last thing that I want to say is that in this type of simulation, we can actually now introduce a more complicated pathway for the kinetics of gelation, because this is a TEM image of the gel formation that you can see. It starts from the surface of the grain, and there are gradients of density departing from the grain that is dissolving, as we would expect. So we can modify this simulation actually to mimic basically this type of gradients. And then we can study the effect of these spatial gradients on the interplay between these spatial gradients and the evolution of these interactions. So here, these are two snapshots of the simulation that correspond to the same type of interaction that I showed you before. So these would be early stages of the iteration, and these would be later stages of the iteration. And they are colored in terms of local density. And so you can see, and this is the case in which we actually have a preferential precipitation of the material starting from the surface of the grains, which are mimicked as the boundary of our simulation box. And so you can see that, in fact, by doing this, we have actually also find out that the early stages type of interaction that leads to these fibrils, this more anisotropic growth of the gel, and this more earlier age percolation, they actually favor basically a type of structure that is less sensitive to these spatial gradients, whereas the later stages of the interactions, they are actually much more sensitive to the spatial gradients, and so the heterogeneity of the gel formed in this case that we had already seen in the other simulation becomes even more enhanced. So again, we can see basically that this effect of the interplay between the specific time evolution of the effective interaction on the way the gel forms, it's confirmed, and it's even more amplified in presence of spatial gradients that can come from the inhomogeneities that exist in the real material. Okay, so now the question is, okay, what can we really do with this type of information? And can you, once that you understand this physics, can you really start to contribute to the discussion on how to improve, for example, durability and resilience of the things that we build with cement? Because in the end, these are very important aspects that we care about for the quality of life that in the built infrastructure, and for the whole economy and ecology of the construction cycle. And so if we now take this model materials and we let them evolve at very high densities in presence of, so like what you would get in the hardened paste, which is what you would get basically in your construction, then you can see that you can identify the pore structure. right? This is what you have here. And you can see that there are some large pores in this very dense material, but there is a very fine network of small pores that are actually all connected. The presence of these pores and the connectivity of these pores is very important for the interaction of the material with the environment and with different degrees of humidity and different type of environmental conditions that can evolve. So identifying this pore network is actually extremely important for understanding the durability and the resilience of the material in the infrastructure. On the right, you can see that we have this material that it's very dense. Here I have this structure which has been colored in terms of the local density. So you can see that the material is very dense. You have parts of the structure that are extremely highly packed, densely packed, but it's also very heterogeneous. And now from the simulation, you can actually compute, just using the particle position, you can compute the scattering intensity that you would obtain from this type of sample and compare it directly with experiments that are shown here. And so you can see that the signal that you get, this upturn at low Q that we obtain from the different degrees of heterogeneity that we have here. In fact, we can do more refined studies and see that this type of upturn comes directly from the presence of these pores, their connectivity and their shape and their surfaces. So we can basically, we have some interesting indication that the structures that we have obtained, calculated in this way, they share very interesting similarities and structural features with the ones of the real material. But of course, you can do more with this type of simulation because you can compute the mechanical properties. For example, here we have computed the indentation models and the hardness by doing different type of computational mechanical tests. And we can superimpose our data with the data from experiments, non-indentation that our colleagues at MIT did. And then you can see that our actually higher densities corresponds basically overlap well with the experimental data, whereas we have a whole range of moduli values that corresponds to lower density gels that are not actually mapped to the experiment. And so what we can do is that we can identify which part of our structure, in fact, it's more relevant to the experiment. And so you can see that, in fact, even in the higher density gels overall, there is actually, there are inner layer of inner parts of material that are actually have higher densities and that are still percolating. And so these are responsible actually for the main mechanical strength that is measured in the nano-indentation experiment. So basically what we are, and for most of the hardness of the material. So what we are also unraveling here is that there is a very dense rigid backbone of the material that it's probably formed in the very early stages of the gelation process that we were discussing before, which then constitutes the part of the material that it's harder and it's stronger, over which the successive process deposit layers of less dense material that then is in contact with the pores. And so you can think now that if you start to think about where are possible origins of plasticity and stress relaxation in this material, and I'll tell you in a minute why, then you can identify with this type of study where plastic processes are more likely to occur, where stress heterogeneities develop in the material. And I'm trying to now go back to the structure and understand the type of stress heterogeneities that you sort of freeze in this type of structure as the gelation process develop. You can clearly see that, in fact, this final structure of the material has this stiffer, more rigid part that is under compression, whereas the softer layer, that are deposited on top during during the gelation process, they tend to be under tension. And so you can now study how this specific sequence of internal stresses that are freezing the material, that gets frozen in the material as the gelation process develops, how also by changing the gelation process, I can actually change this type of stress heterogeneities, and then therefore then change some aspects of the linear and nonlinear behavior of the mechanics of the material, which can go all the way to creep and crack healing, and therefore increasing the material toughness. Okay, so basically, if I wrap up all this together, what I told you is that there is actually understanding cement as a material in the context of construction, it's a unique opportunity to try to say something and to contribute to the question of how the sustainability of the construction industry, and how can we actually change things in a scientifically guided way to make a difference in reducing CO2 emission of this very important industrial sector. What I showed you is that, in fact, if we start to approach with a physics perspective the cohesion of the material, we can understand that actually water plays a very important role, and we can understand quantitatively that through water the ion specificity of the cohesive forces, nanoscale cohesive forces in cement, and how the evolution of the forces actually depends on the water confinement and on the ion water structuring. And I would say that this is really a first step, maybe the zero level step, to try to now design cements that are greener and can still perform in a similar way. From this information, we can actually understand, then build a new approach at a more mesoscale level to rationalize what happens as the nanoparticles start to gel, and how the development of the microstructure of the gel then determines the porosity, the mechanical strength of the material, and how this development allow us to identify new pathways to change material properties and design mechanical performances during cement hydration. And then finally, I've shown you how really this type of approach, in fact, it simplifies a lot of things about the material, but it gives us insight into how stresses get built in the microstructure, how the porosity of the microstructure can change the way the material interacts with the environment, and therefore also with the environmental condition, and gives us possibly a quantitative new pathway to design really the mechanics and the resilience of our infrastructure in a more sustainable way. So with this, I would like to thank my collaborators. Most of the work that I showed you has been from my former PhD student, Ame Goyal, that is now a postdoc at NIST, from Caterina Ioannidou, that was my previous student, my first student actually, working on this at ETH in Zurich, and she's now faculty in France, and a number of very amazing collaborators I've been lucky to work with. And with this, I would just like to thank you for your attention, and I'm happy to take any questions.
Okay, thanks very much, Emanuela, for a soft matter take on a very hard and stiff material. So we now invite questions from the audience. We have a raised hand. It's Nuno. Nuno.
Hi, Emanuela. Thank you very much for your talk. Very clear. One question: what is a typical time scale for the evolution of these forces, and how this competes or compares with the time scale for drying?
Okay, so that's a very good point. In fact, cement doesn't really dry. This is a very important thing because we say cement is drying, but in fact, cement is setting. And water actually doesn't really go away. The part, of course, there is some drying from the surface, but that's a minimal amount. Most of the water remains in the structure, and actually it's used to develop those cohesive interactions that I was talking about. Mm-hmm. And that's the reason why you can make cement and harden cement also underwater, right? Okay. So basically, the process that I was describing, it's what happened in the material, and it's basically, of course, it's more complicated than that. But it's basically independent from what you say is the drying, because the drying is a very small effect. Okay. But of course, the amount of water that you use, it's a very important. As a very important role, because it changes the dissolution and the homogeneity of the precipitation of the cement hydrates. And in fact, it's the big evolution of the industry has been to try to reduce the amount of water that you use for two reasons. Because water is a resource that, of course, you don't want to waste. And I mean, it's not a waste, but you have to deal with the limited amount of waters in certain conditions. And in principle, you would like to use less. But also, when you have a lot of water, this makes your paste more flowable, so it has interest in that side. But because then the precipitation is more heterogeneous, then you end up with a material that is less heterogeneous. It has more tendency to crack, and so then the evolution of the industry, which has gone through mainly using additives that can keep the material, the paste, flowable with a relatively little amount of water, has gone in the direction of reducing more and more water. What is interesting, the amount of water that you use in the beginning. What is interesting is that actually we find that the water that is involved in these cohesive forces is really tiny amount of water, which then makes it interesting for all this debate about this and about making cement with in situations where there is very few water, very little water.
I just have a second question. That is, you have shown in the beginning that you need a certain degree of confinement in order to form these water structures that are necessary.
Water ion structures, yes.
To keep the cohesion. Mm-hmm. But in order to do that, you need to bring this surface together.
Right.
So in the simulation, it's easy. You probably fix the position of the surfaces.
Definitely, yes, we know how to do that.
Exactly. So in reality, what is keeping this surface together while this structure is formed? Because
it's because basically you have to imagine that you have the grains, and then the grains progressively dissolve, and this material, it's precipitating continuously. So the number of nanoparticles, if you want, the volume fraction of the nanoparticle, it's increasing over time. And so the thing that we mimic with the change of confinement, it's basically the densification, should correspond to the densification process of the system, right? So you have a larger amount of nanoparticles that is produced over time, and this is basically makes the distance between nanoparticles shorter and shorter.
But the surface charge is still is always the same, or is also evolving?
No, at the same time, the surface charge is.
Okay. Otherwise, the energy cost of putting another particle there will increase. Okay.
Yes, and so one signs of that, there are many studies of this type of kinetics, but one that it's typically shown is basically this this is the heat flow during that corresponds to the reaction, comes from the reaction of the formation of CSH that is exothermic. And so basically this, from this type of curve, you can turn this into a type of hydration, counting the amount of hydrates that you produce. And so you can see, maybe I even have data, let me see on this. Yeah, so basically this is what you have here, right? So from the calorimetric measurements, you extract this degree of hydration, which is the amount of hydrate of basically of nanoparticles of hydrate silicate, calcium silicate hydrate that you produce. And this over time increases with this sigmoidal fashion. And here we have, I've compared this with the increase of the volume fraction in our simulation. And you can see that you get a similar shape with what you see in the experiment. So there is some aspect of this kinetics that we are able to recover.
Yeah. Okay, thank you very much.
Right, thank you. Now we have a question from Margarita.
Oh, hello, Emanuela. Let me put my video on. Okay. I have a couple of questions. One, oops, my video is sort of not okay. Nice to see you, nice talk, but there is something I didn't quite understand. When you have your potentials, your effective potentials that change with time,
yes,
from the repulsive to the fully attractive,
right?
How do you choose those times? I mean, to me, it seems like a continuous process.
Yes, you're right.
Separation time scale. So how do you do it?
Yeah, in fact, I have to confess that we don't do it. So what I showed you, what we did is this first study where we actually fix one type of interaction, and then we watch the relation with that type of interaction fixed. Okay, so we don't change it. And we did that because we wanted to understand if I have just one type of interaction, which type of gel would I get with the different, changing the gelation rate. Once that you understand that, and then you get this picture, okay, so the time evolution must be important, then you would like to go back and do exactly what you said. So to actually be able to mimic a process in which this evolves over time. And we have done it, like qualitatively, just to make nice movies for us, but it's very tricky to understand how to, because in the simulation, of course, you can do it in many different ways, and how do you choose things in a way that makes sense. So one thing that we have identified, also one strategy is basically to, the idea is to, now that we know how the type of interactions are evolving, depending on the ionic composition, we can go back to data that from the experiments have monitored the evolution of the ionic composition, and then understand what could be, a reasonable, a realistic way, right, for which this can evolve. This was, in fact, I presented you the story in this way, but of course, we never think in a linear way, right? So what we did was, historically, was first to study the gelation. And then when we saw the effect of the interactions, then we started to go back to and try to understand the interaction from first principle. And now that we have that, we can try to mimic that type of process really fully. And then for now, we have done it very, very, rudimentally.
No, I think I understand. I have another, it's sort of unrelated, or at least seemingly unrelated question. And you mentioned at the beginning that for you, the surfaces, the confining surfaces were just the electrostatic, the ionic. There was no roughness whatsoever, no structure.
Yeah.
But you seem to be modeling everything at a much smaller scale. I mean, like the water with those micro.
Yes. That's a very good point and a very valid question. And so there are studies, of course, of the atomistic structure of these surfaces. So it's just that, of course, the problem that there is that this material is already very complicated on very small scale. So it's not that you have just a nice crystal, right? So but which again goes even more in favor of your point, because then we know actually that these surfaces are very heterogeneous. And so the problem is that when you describe all the degrees of freedom, when you consider all the degrees of freedom you have to put in there, then it becomes basically impossible to do the study that we have done, right? So that's why we have decided initially to simplify our surfaces and just consider the surface charge. However, then once we have done the simulations, we were able to compare our results with what people see in the atomistic simulations, where they basically look only at the situation where you have the highest confinement. So the surfaces are very close, so you have very few water molecules that are left. And now if we go back, we actually can see that the type of water structure, the amount of water, the coordination of water of the ions that we get in those conditions is actually in very good agreement with what is obtained with these atomistic simulations for the highest surface charge. So this suggests that we have taken a very strong approximation, but it's not too bad for the moment. And I think the way I can understand that is that actually because the surface charges are so high in the end. Yes. And so basically, do you see what I mean?
Yes, so you're saying that actually the cohesive energy is completely dominated by the
electrostatics. Exactly. That's what we learn from there. I don't mean to say at all that surface heterogeneities are not important. For example, we found that the arrangement of the ions that we obtain, of the ion water structure that we obtain, it's very similar to, it is a lattice that it's sort of registered, completely anti-registered with the lattice in the other layer. And it's very similar to the ground state found by our theory colleague, that they were just looking at the electrostatic problems with just the ions between surface charges with this very, in this very strong coupling regime, which suggests again that basically the electrostatic is what becomes more dominant at that point. But certainly the presence of surface heterogeneities will change where your lattice gets stuck, right? And it can create spinning sites. And so there is a lot of interesting things to understand there.
Well, thank you very much.
Okay, thank you. Do we have any more questions? I don't see any more raised hands. Any more questions? Your last chance. Okay, no more questions, so let's wrap up. Emanuela, thanks very much for a very interesting seminar.
Thanks to you all.
Thank you all for coming. And next week, there will be no seminar because it's a public holiday. So we'll be back the week after that on Thursday, the 17th of June at our usual time, which is 10 a.m. Lisbon time. So thank you all for coming and see you then.
Thank you. Bye-bye.
Okay, so recording stops now.